Hello, I'm Israel. Today I will talk a paper. It's called Comparison of some conformal quantile regression methods. So this paper is come from here. This is the Metal, Cesar, and Candace. Okay, so I just put some important things into my report. So okay, so So I just read the paper. This week I just read the paper, a comparison of some conformal quantile regression methods. And in this paper, they introduce and compare some conformal quantile regression methods and show the related theoretical analysis and simulation results and real data analysis. So I will try to explain and compare these different conformal quantile regression methods. So, okay, so before we talk some methods, we will talk some settings first. So given that the n points xi, yi from 1 to n with yi and xi, we consider the problem of constructing a prediction interval for a new point yn plus 1 based on the observed value of xn plus 1. Assuming only that xi, yi from 1 to n plus 1 are drawn exchangeability from some common distribution pxy. So based on this, so the conformal inference addresses this problem by constructing an exact marginal prediction interval, c hat alpha xn plus 1, such that the probability of yn plus 1 belongs to this prediction interval is larger or equal to 1 minus alpha. So and this one will rely only on exchangeability of the n plus 1 points. So ideally, prediction intervals should be as narrow as possible while maintaining the coverage. So we let us denote by q alpha n plus 1 is the alpha quantile of the conditional distribution of y given by xn plus 1. Then the desirable oracle prediction interval will be c alpha oracle equals to the lower bound will be q half of alpha and q1 minus half of alpha, and this is the upper bound. So by construction, this is a narrowest symmetric prediction interval that has a valid coverage conditional on the value of xn plus 1. So here he also explained what is symmetric. So he says a prediction interval is symmetric if yn plus 1 is equally likely to be a smaller or larger than predict. Okay, so this is the basic settings. So if we understand this one, so we can go down, we can talk about what is conformal quantile regression. So throughout this paper, we follow that the split conformal approach to conformal inference, since it is computationally feasible even with large data. That means it will use the split conformal methods to do this conformal quantile regression. So they have several steps. The first one will be split the data samples into two disjoint subsets, L1 and L2. So the L1 will be a training data, and L2 will be celebration data. Okay, so the second step will be the lower and upper quantile regression function are fitted on the observation in L1. And then the third step will be the estimated quantile function are used to compute a conformity score for each I belongs to L2. So we'll put the celebration data into the quantile regression function and to get the conformity score. And this conformity score will be the maximum of the q hat half alpha minus yi, or the yi minus q hat 1 minus half alpha. And then we can get the Q hat 1 minus alpha with the ECQR and L2. This is defined as the cell function of 1 minus alpha times absolute value of L2 plus 1, largest element of the EI. So the conformal prediction interval for xn plus 1 will given by this one, C hat alpha CQR equal to Q hat half of alpha minus capital Q hat 1 minus alpha, and the upper bound will be Q hat 1 minus half alpha plus capital Q hat 1 minus alpha. So this method denotes the CQR. So the CQR shows that the C hat alpha CQR has the marginal coverage at level 1 minus alpha. Okay, so this is the basic method of the CQR. And there are two variations. One is CQRM and another one is CQRR. So the two of the variation, the overall step is similar, but the main difference is how to get the conformity score. So like this one, CQRM. So if we instead the third step is to compute the conformity score. So that means the CQRM, the conformity score of the CQRM will be this one. They will both of them are divided by Q hat 0.5 minus Q hat half of alpha, and the other one will be Q hat 1 minus half alpha minus Q hat 0.5. So Q hat 0.5, it is an estimated median regression function obtained with the same algorithm as the Q hat half of alpha and Q hat 1 minus half of alpha. So the conformal prediction interval will be this one. It will be Q hat half of alpha minus a triangle hat, and the upper bound will be Q hat 1 minus half of alpha plus the triangle hat, and the triangle hat alpha lower bound will be the capital Q hat 1 minus alpha with ECQRM and L2, and it will times the denominator, and also the similar, the triangle hat alpha upper of CQRM will be the capital Q hat 1 minus alpha times its denominator. So also this can show that the C hat alpha CQRM also has a marginal coverage at level 1 minus alpha. Yeah. So you can see this one. You have to compute the median regression function. So this will be a little bit trouble. So they also think another modified version. So this modified version of CQRM that does not require estimating the regression median. So this one will be the CQRR. This is based on the following conformity scores. So the main difference of that will be the denominator. It will become to Q hat 1 minus half of alpha minus Q hat half of alpha. And you can see that both of them, the denominator are the same. So we can get a CQRR prediction intervals. That will be Q hat half of alpha minus triangle hat alpha CQRR, and the upper bound will be Q hat 1 minus half of alpha plus the triangle hat alpha CQRR, and the triangle hat alpha CQRR will be the capital Q hat 1 minus alpha with E is equal to R and L2 and times the denominator. So this can also show that the C hat alpha is equal to R attains the marginal coverage at level 1 minus alpha. Okay, so this is the algorithm I just copied from the paper. So the input will be the data and the new sample xn plus 1, and the proportion of data of training, gamma, and the quantile regression algorithm, and the 3 different methods, CQR, CQRM, and CQRR, and coverage level alpha. So the procedure is like that. So the first step is here, randomly split into L1 and L2. So the L1 will be the n times gamma, and the L2 will be n minus L1. And the second step will feed the quantile regression functions. Q hat half of alpha and Q hat 1 minus half of alpha. So so we can see the first one. If this one equals to CQR, so we can get the third step. So we can get the conformity scores EICQR for each I belongs to L2, and we can compute the capital Q hat 1 minus alpha, and the last step will compute the prediction interval C hat alpha. So the other two will be similar. So only this one, CQRM, before the third step, we need to compute the median regression function. And we also get the conformity scores, and last one will get the prediction interval. And also the CQRR is similar. We also can get the conformity scores, and we can get a prediction interval. Okay, so the next part I'll talk about is theoretical analysis. So before we talk about the theoretical analysis, we have 3 assumptions. And also these 3 assumptions is copied from the paper. So the first one is IID. So the points are drawn IID from the same distribution. Okay, this is the first one. And the second one is regularity. So the probability density of conformity scores, depending on the conformalization methods in algorithm 1. And it's bounded away from 0 in an open neighborhood of 0. And the third assumption is consistency. So we denote by n the size of the training data set and used to feed the quantile regression function Q hat, and let x be the new observation independent of L1. And the assumption is that for n is large enough, so we can get these 2 equations. Yeah. So we can get this theorem 1. So under these 3 assumptions, the conformal quantile regression bands C hat alpha obtained with algorithm 1. So we satisfy L of C hat alpha and triangle and C alpha oracle xn plus 1 is equal to OP1 as L1 and L2 becomes to infinity. The LA is the Lebesgue measure of the set A, and triangle is a symmetric difference operator. So this theorem is work for these three conformal quantile regression methods. Both of 3 are all of 3 are good to use for this theorem. Okay, so also the next one is the definition of asymptotic conditional coverage. So we say that the sequence C hat n of random prediction bands has a asymptotic conditional coverage at the level 1 minus alpha if there exists a sequence of the random sets such that the probability of the x belongs to this set is 1 minus OP1. And then we can get the soup of the probability of y belongs to the c hat n given by x. And this probability minus 1 minus alpha is equal to OP1. So this is the definition of asymptotic conditional coverage. So the next part we'll talk about some experiment results. So the experiment results, you have two parts. One is simulation parts, and the real data parts. So I think we can just go from the paper. I can show you in the paper. So okay. So we can just get smaller. Okay. So so we can get both of the simulation and real data. They use the quantile. They use two settings. One is quantile regression forest, and the quantile regression forest they fit 1,000 trees, and set the other tuning parameters to equal their default values. And the other one is neural network, and they use 3 fully connected layers and ReLU nonlinearities. So they use the these two settings for both simulation and the real data analysis. Okay, so the simulation data will get the x will be the uniform distribution from 0 to 1, and the dimension will be 100, and y will be this one, f beta plum x plus epsilon times this 1 plus the square of the beta plum x with square, and f of x equals to this one, and the beta plum will be this one, and this epsilon is independent standard Gaussian noise. Okay, so also the proportion of observation used to train the training data will be 0.75, and the test sets will be 2,000. And this experiment will repeat for 100 times. So, and also they show the oracle prediction band will be this one. Yeah, it will be around 8.91. Okay, so you can see these results. The sample size from 50 to 50,000, and we can see as the sample size become larger, and the average length will more near to this 8.91, and we can see that this CQR is better than CQRM and CQRR, and also we can see CQRR is also a little better than CQRM. And for the coverage, we can see the three of them looks are similar, right? But when the sample size becomes larger, and the coverage will be very, very near to 0.9. Okay, so this is the simulation data, and the next one will be the real data, and they use least data, least real data to do the real data analysis. And here's the number and the dimension, and also so this data accepts homes. Homes is here. They randomly hold out 20% for a sample for testing, and divide the remaining observation into two disjoint sets. And They will explore different values for the fraction of samples used for training and celebration. So this is for the pruning parameter, and they will compare which gamma is for the best. The home data will be used here. They use 3,613 test samples and train the black box at 15,000 samples and conformalize on the remaining 3,000. And they repeat 10 times and starting from the data splitting. So they can get results from here. So we can see the average length here, and as we can see, the CQR have the shortest average length. Has the shortest average length, and the CQR and CQR is better than the CQR and CQRM, and also for the coverage, I think all three looks similar, right? But the average length is significantly better, and we can see from here. This is from one of the data. Let me check. This is the community data. Okay. So this is the community data for each pruning parameter. So we can see this is random forest for tuned with CV and nominal level. Also the neural network is here, and this is the pruning parameter from gamma equals to 10 to 98. So from here we also can see the CQR is the best, right? And also we can see the gamma will be better from 70% to, I think it's 70% to 90%. It will be the best. So we can see these results. So the first, the width of the coverage of the conformal prediction bands approach those of Oracle as the sample size increase. And the second, the CQR typically produce narrower bands compared to other methods in both simulation and real data. And the next one, the CQRM methods sometimes produce very wide intervals because the denominator can be close to zero. But the CQR methods is less susceptible to this problem because the denominator in conformity scores is larger. So we can see a CQRM. This denominator will be this one. Sometimes the both quantile regression will be smaller because you only from the median to half of alpha. But the CQR will be the width will be 2 times larger. So the performance of the CQR looks more stable, and also you have a little bit better, right? So here we can see sometimes this one CQRM, the average length will go to 300. This is very large, right? That's just because the denominator is too small. So the value of this will become very large. Okay, so the last thing we can get at the premium parameter gamma shows the proportion of the training set and celebration set. And from the results for the paper, it finds that with fixing the proportion of training set gamma between 0.7 to 0.9, it can achieve a reasonable compromise of the all data sets. So from this parameter, we can get the training data set, the proportion of the training data set will be 70% to 90% will be the most ideal case to do the analysis. Okay, so this is the introduction of this paper. So if you want to know more about this, you can just see that you can just see that paper. It will be interesting. Yeah. Okay, so this is my today's talk. So see you next time.